Hello everyone, this lecture is about plate tectonics and forces that drive plate tectonics. As we discussed in the earlier lectures, plates are moving at the surface of the Earth and they're floating on top of mantle that is convecting. We have various types of tectonic deformation along the plate boundaries, such as subduction margins, transform fault, and ridges. The deformation requires the application of a stress, and this is what we discussed in the earlier lecture. But in order to have stress, we also need to understand what are the forces. And so the question here are what are the forces that cause tectonic motion, stresses, and deformation in the Earth lithosphere. So let's start with Newton's second law of motion. So you have here the sum of the forces, or the resulting force, is equal to mass times acceleration. Forces are unit Newton, mass is in kilograms, A is the acceleration, so it's the time derivative of a velocity. Now, let's ask the question, what about inertial forces? So one can compute the role, or one can estimate the role of inertial forces for geodynamic motions. So let's compute the power. The power is the effect of the resulting forces times the distance over which the force has been active. So we have a delta L. Here is a displacement, so we can compute the displacement. It's the time integral of a velocity. The velocity is the acceleration times time, so we can time integrate AT, and we get AT squared divided by 2. So we can recompute here the work. So the work is the sum of forces times AT squared divided by 2. If you substitute the mass times acceleration instead of the force, you will get acceleration squared also. So you have mass times AT squared divided by 2. AT is the velocity, so the work here is velocity squared divided by 2. Where am I getting to? This is the definition of the kinetic energy. So the kinetic energy of an object is mass times velocity squared divided by 2. It's the power of the resulting force. So let's evaluate the kinetic energy of a tectonic plate. So we will assume that a plate moves at 5 centimeters per year, and we will apply this formula for kinetic energy. Half times meter times velocity square. We take a plate that has 2000 kilometer times 2000 kilometer surface and a thickness of 1000 kilometers. So here we compute the volume. We give a density of 3000 kilogram per meter cube times the velocity square. That's 1.5 kilojoule. So the question is this a relevant quantity? Is that a large magnitude? So one can try to compare with a car, for example, and one may ask the question, how fast should a small car of 1 ton have to drive to reach the same kinetic energy as a lithospheric plate? So one can solve for the velocity here using 1 ton and 1.6 kilojoules here. So it's square root of 2 times 1.6 kilojoule divided by 1000 kilos, and that's 6.43 meters per second. So it's really not a lot. In a way, this indicates that the kinetic energy and the related inertial force do not matter for tectonic motions. So the inertial force is tiny on the geological timescale, so we can make the assumptions that MA is more or less equal to 0. So we can use the sum of forces is equal to 0. So this means in a way that the plates move with a steady velocity if we consider geological times, not over the earthquake time scale. But now you may ask the question, you all know the history of the Indian plate. It's been moving over tens of million years towards the Eurasian plate in order to enter into collision. And you know that the plate velocity has been varying quite a lot throughout geological time. So you have a reconstruction here of the plate history from 60 million years to 20 million years, and you see fluctuation of this velocity. And quite a bit of fluctuation. So between this point here, you had 4 centimeters per year, and here it's 22 centimeters per year. So is it really steady? Let's try to compute this. So we take the extreme case, we select this time frame here. We have a change of velocity from 4 to 23 centimeters per year, and we assume it takes place within 1 million years to make the case really extreme. Let's try to compute the acceleration. So we approximate the acceleration by a difference between the two velocities, and we obtain, and we divide it by delta t, so delta t would be 1 million years. That gives a number on the order of 10 to minus 22 meters per second square. Now we have an acceleration. We want to compute the mass. So first we take the surface of the Indian plate. That's this big number here. We assume a thickness, and we assume a density again of 3000 kilograms per meter cube. So the mass is that big number, and you see 10 to 21. So we are going to make the product between the mass, which is density times volume, 10 to 21, to acceleration, which is on the order of 10 to minus 22. The resulting inertial force, MA, is 0.7 Newton. So it's not zero, but one again has to compare with other forces into play. And remember the lecture about the stress. A human on 70 kilo in the under gravitational acceleration of 10 meters per second square exerts a force, mg, of 700 newtons. So that is dramatically larger than inertial force, even in the most extreme case here. So indeed, we can assume that plates are moving at a steady velocity. And if we want to understand how plates are moving, we need to look somewhere else. It's not the inertial force that is driving plates. So we simplify the statement that sum of forces is equal to 0. And what are the forces that are left into play? Of course, you remember the lecture about isostasy. In that lecture, we introduced body forces and surface forces. And first, we discussed about body force. So the body force is a force that acts through the volume of a body. So for example, gravity will be one of the main cause of body forces, or one of the main body force. So remember our block here representing a column of lithosphere is undergoing gravity. It has a density, and so we can compute the body force which is associated to that. It's simply mg. Gravity will matter a lot for tectonic motions. We come to this in a couple of slides. A surface force is a force that acts across or along the surface of a body. There are normal force, those that are normal, perpendicular, and shear forces, those that are tangential. The normal force is caused by a stress, which is normal to a surface. So remember the example of last time. The normal force here is related to the product of the normal stress, sigma yy, times the surface, delta A. It is the normal force in reaction to the body force here. The balance of these two forces will create equilibrium. There are also shear forces. These are the ones that are caused by a stress which is tangential to the surface. For example, if you would have a flow in that direction, it would exert a shear force or a drag at the base of this column here. We'll see that shear force or drag forces, they will matter for tectonic motions. One can compute or estimate the shear forces by integrating the stress over the surface of the body. So let's have a look at this sketchy view of the Earth's internal dynamics. What are the forces into play? So there will be body forces and there will be surface forces. So you see two important body forces here. This is the slab pull. That's the force exerted by a slab which is sinking into the mantle under the gravity. It's supposedly denser. There will be ridge push. That's a force exerted by the ridge because we have here a high topography or topographic gradient across the ridge. There are surface forces, and the surface forces are mantle drag, slab resistance, and suction forces. So if there is a fluid which is being sheared because the plate is moving, so the mantle here is being sheared, there is a shear stress. This induces a mantle drag. If there is a plate motion, if the trench here is moving, it induces a suction of the trench. And the slab, of course, there is a resistance to the penetration of the slab. This is also a surface force at the tip of the slab. So in tectonics, it's common to estimate forces in unit Newton per meter. In other words, we have a 2D vision. We compute, we make force estimation by or per 2D cross sections through the Earth, as on the sketch here above. So all the estimate of forces we make in the next slides will be in units Newton per meter. So let's discuss first about the slab pull. So the slab pull is a gravity force. It's a body force. It's exerted by a subducted slab. So the slab here is sinking into the mantle. It is colder than the surrounding mantle, and the density depends on temperature. The density is larger because the slab is colder. So that's for the principle. In a way, the slab pull force is just the slab being denser than the surrounding, so it sinks. Like when you would drop a rock into the water, it would sink down in the water. How to estimate these values? Then to estimate the gravity force, we need to know the density difference between the slab and the surrounding mantle, that's delta rho. G is the gravitational acceleration, and S here would be the surface. We are working in a 2D section, so we use the surface instead of the volume here. This will give us a force in unit Newton per meter. So density of slab minus density of mantle times rho G H times L, and this gives us a slab pull force. Here, with these parameters, we get something on the order of the 10 to 13 Newton per meters. The ridge push force is a body force. It is actually a gravity force which is exerted by the mid-ocean ridge. The ridge has an elevated topography because mantle is being upwelled at the mid-ocean ridge, and this creates a lateral density gradient between mantle being high and water being next to it. So it makes a lateral density gradient which induces a net horizontal push force. So how to envision that? You can think if you would have a glass with honey and water. Honey is denser, it's sitting at the bottom. If you dip the glass to mimic the rise of the mantle in the mid-ocean ridge, and you put back the glass on the table on a flat position, there will be a force that will restore the honey back, which pushes back the honey to horizontal position. So that's an analog configuration to a ridge. where the mantle is being upheld and is trying to restore its horizontal position at the same time by pushing the plate. We will now make a first order estimate of the ridge push force. So remember, it's a body force, a gravity force. So we will need to know the difference of density, the acceleration of gravity, and the surface of the object to compute the force in Newton per meter. So the density contrast of interest is the density contrast between mantle and water. G is known, and now we need the surface. We approximate the shape of the ridge by a triangle here. So the surface is h times L divided by 2. And if we plug in these typical numbers here, we would obtain a push force which is on the order of 10 to 12 Newton per meter. One has to realize that this force is actually caused by lateral density gradients, and this similar type of force can be expected in regions of the Earth where there are large topographic gradients. So, for example, on the boundaries of a continental plateau or along the boundary of a subduction trench. These can induce forces of the same kind. Now the mantle drag. This time the mantle drag is a surface force. It's a shear force which is exerted at the plate-mantle interface. So we have a plate, it's moving with a velocity, and below there is a fluid which is being sheared by the motion of the plate. To make a first order quantification of the shear force, we need to know about the shear stress. And we need to know about the mantle viscosity to compute the stress. So let's go for a first order estimate. To compute the surface force, we need to know about the stress and the surface of the plate over which we want to integrate this stress, L. So let's first estimate the shear stress, and to estimate the shear stress we need to know about the shear strain rate. We can use the formula from the preceding lecture. We have 1/2 of dvx dy plus dvy dx, which is here 0. We approximate dvx dy by the x divided by h. So it means we take the velocity of the plate at this point minus the velocity of the plate, the velocity in the mantle far away from the plate, it is 0, and it's divided by the distance, Vx divided by h. This gives an estimate on the order of 10 to minus 14, second to the power minus 1. And now we compute the shear strain rate, 2 times viscosity times strain rate. This gives an estimate on the order of 3 megapascal. If we compute the drag force by assuming a plate length of 5,000 kilometers, we obtain an estimate also of 10 to 12 Newton per meter. Now, there are also suction forces, and these are surface forces that are caused by attraction. So the mantle flow is caused here by a sinking slab. You have this sketch here where you can imagine the mantle is here, there are plates at the surface, and there is an object which is sinking there like a slab. When the slab is sinking, it induces flow of the mantle, and this flow causes a shear traction at the base of each of the plates, and then can cause a motion of the plate. So this is very similar to a mantle drag. The suction force will be a drag force exerted on the plate. Other type of suction force may be caused by subduction dynamics. So for example, here we have the trench retreat. So you have to imagine the plate here is subducting, but the trench is moving towards the right. This will induce a suction force. And 2 types of suction force. So first there will be the shear force due to the motion at the interface of the slab. So that is a shear force which is along the interface here. But there is also a normal component, and this is the trench suction force which is normal to the subduction interface here. So these are all the forces we've been discussing so far. There are body and surface forces. The body forces are gravity forces, and the surface forces are drag or suction forces. And the question one may ask is, which one is the main driver of plate motions? So let's get a hint from basic dimensional analysis. So we now try to make a simple balance between gravity and drag forces. So first, we make an estimate of the thickness of an oceanic lithosphere. And as you know, the oceanic lithosphere thickness depends on time. It's related to cooling of the oceanic floor. So one can estimate D as square root of kappa times T. This is the time dependence, and kappa is the thermal diffusivity. And when one may substitute the time by length divided by velocity. Now we want to scale the buoyancy stress, and for this we will use the thickness D and a temperature dependent density. So buoyancy stress is density, which is temperature dependent times G times D. How to compute temperature dependent density? We have to formulate it this way. Rho 0 is the reference density, alpha is the coefficient of thermal expansivity, and delta T is the temperature difference. So we have now these expressions, rho 0, alpha, delta T, G, D. And D, we've scaled it already. The last thing to do is to compute the shear stress. The shear stress scales with the thickness over which we compute the velocity gradient, and the mental viscosity, as we did before. So 2 times eta times shear strain rate will be eta times V divided by L. So we have all of this. Let's equate the two stresses. B is equal to sigma. We have now one unknown. We want to solve for the plate velocity. And one can express this plate velocity as L times this ratio here to the power 2/3. One last thing to do is to plug in reasonable numbers for all of these quantities and solve for the plate velocity. And you will see that if you remain in a range of realistic numbers, you can obtain plate velocities on the order of 10 centimeters per year. So this scaling approach from dimensional analysis is a very good first order estimate of plate velocities. It also means that buoyancy and shear forces, they will be sufficient to explain at first order the plate velocities. Nowadays, one can go much further, and this is an example where models have been used to make prediction of plate velocities over the whole Earth. So here you have the observations, so you have the plate velocities from GPS. You have all these arrows, and the aim of a model is to try to reproduce the pattern. And these models, they can be run with by including some of the forces, so some forces or not. So here you have the slab suction only, here you have a slab pull only, and here you have a model that combines both slab pull and slab suction. So you see that these models, which has both the body and the surface force, best fit the observations. So the best models combines both types of forces. Another approach to study the relationship between plate velocity and forces is to use a statistical analysis. And this goes back to 1975, where Forsyth and Ueda, they presented a study in which they basically make a correlation between the plate velocities and the plate features. What do we mean here by plate features? These are some parameters. The first parameter of interest is, of course, a kinematic parameter. That's the plate velocity. And the plate features are, for example, the surface area of the plate or the percentage of continental lithosphere on the tectonic plate. So these relate to surfaces. Then we have parameters that relate to boundaries. The percentage of subduction boundary along a plate, so for example here, versus the percentage of ridge boundary, or the percentage of transform boundary right there. So these are the different parameters that will be studied in the correlation. So first, one may ask, do we see or can we guess an effect of mental drag? For this, one would expect a correlation between plate area and velocity, because the drag force would be proportional to the plate area. So that's the correlation between area and plate velocities, so from 0 to 10 centimeters per year. And you see here about 13 independent plates. For example, the Eurasian plate is here, the Pacific plate is there, Indian plate, Arabian plate. These are the area, and there is no apparent correlation between area and velocity. So this may indicate that mental drag may not be the major driving force. Does ridge push drive plate motions? So one would expect a correlation between the percentage of plate boundary, which is a ridge, and the velocity. So that's the data. This is the percentage of ridge length and the plate velocities, and we also do not see an obvious correlation on this diagram, so this may also indicate that ridge push may not be the major driving force. One interesting parameter is the effect of the continental area. So here we observe the percentage of continental area onto the plate. So some plates have no continental area, such as these ones. There seems to be an anti-correlation between plate area percentage and plate velocities. So this means that the plates that have the largest continents, they're also the slowest. And now finally, does slab pull drive plate motions? For this, we would expect a correlation between subduction trench length and plate velocity. And this is actually what we see on this diagram. The plates that have a very few subduction or no subductions are slow, while the plates that are surrounded by subduction boundaries are fast. So that's indicating a role of the slab pull potentially. So the whole data set is on this figure here, and what you can see, these are the different parameters. So you have the plate velocity area, continental area, subduction boundary, ridge boundary, and transform boundary. And the color indicates the amount of correlation. Of course, each parameter correlates 100% with each other, but if you look at the correlation between the different parameters, you see the red spot and the green spot. These are the two, the anti-correlation and the correlation between plate boundaries and parameters. So then this indicates that slab pull is an important parameter, because in a way the plates that are the fastest are the one that has the most subduction, but also the plates that are the slowest are the one that have the most continent. And this is because continents are difficult to subduct because they are buoyant. So both this correlation and the anti-correlation here, they're indicating us that the role of subduction is primordial for plate motions. So as a conclusion to this lecture, we saw that the tectonic motions are driven by body and surface forces and not by inertial forces. The body forces are mainly gravity force, and the dominant force here is the slab pull force. Thanks a lot for your attention.